Okay, it's 1 o'clock, so why don't we get started? I just have a few slides left from last class that I want to finish up, and then I'll open up today's slide deck. So we were talking last time about naive Bayes, and I ended when we got to this decision theory part of the lecture, which is to say if you make a grid of what you predict and the true label for binary classification, you can have these false positives, false negatives, true negatives. And as we talked about last time, the level of unhappiness or the score, the badness score, may be different in each case. And just to reiterate from last time, for example, letting a spam message in is not as bad as keeping a not spam message out. And so that's reflected in this 10 where you predict not spam, but it is, and then 100 where you predict spam, but it isn't. And these are kind of loss or costs, as we call them. So the bigger the number, the worse you view the situation. And we have this probabilistic way of handling it, which is to say what's the expected value of the cost. And so what we want to do there is compute what is the chance that we'll make these two different kinds of errors. And so what we can do is, by incorporating this information, we'll bias what we predict. So maybe we think probability of not spam is higher. Probability of spam is higher, but we may still classify it as not spam just because in the expected cost will be lower in that scenario. So for example, we want to compute the expected cost if we're classifying spam, given that we don't know what the true label actually is, we can say, well, what is the probability that we make that kind of error times the cost of making that kind of error plus the probability of making the other kind of error times the cost of making that other kind of error. And what it works out to be is basically a weighting of the probabilities that we already had. So I can do this for predicting spam. I can do this for predicting not spam. In each case, I get an expected cost. And then I'll take the lower expected cost. And that'll be my prediction. So it's a bunch of probabilities. But at the end of the day, we're really just weighting. We're incorporating these costs by weighting our outcomes. So what's the probability of these various scenarios? And what's the cost of these various scenarios? Gives us the expected cost for predicting spam and the expected cost for predicting not spam. Okay, so something that we don't really go into much in this course, but I just wanted to have you guys be aware of its existence, is this notion of precision and recall. So precision being, if I classify something as spam, what is the probability that it was actually spam? And these TP and FP refer to true positives versus false positives. So this is true positives means the number of things that are spam that I say are spam. And then we're adding true positives and false positives, which is the total number of things that I predict as spam. So if our method has high precision, it means that the filtered out messages are really likely to be spam. And we can also compute the recall, which means that most spam messages actually get filtered out. So what would be perfect is if these were both equal to 1, meaning I have perfect classification. But these numbers can be more informative and more meaningful than just how many correct am I, because it distinguishes between the different types of errors I can make. So you may also come across a precision recall curve where you have recall on one axis, precision on the other. And you can visualize the trade-off between these two for various settings of your method. And there's more on this in the bonus slides. I'm not planning to go into it, but just again, so that you have heard of these things, I think that's important. Another thing that is worth having seen is this issue of unbalanced classes. So unbalanced classes means that in your training set, you have much more of one class than the other. So on the slide, we have most of the time you don't get sick. So maybe in your training set, 99% of the days we're not sick. And therefore, classification accuracy could be a very misleading performance measure, because you could say I got 99% accuracy, but actually your classifier was just predicting not sick and it wasn't even looking at the features. So other performance measures like precision, recall, etc., would allow you to see that, oh, of the times I'm sick, I'm actually getting it wrong half the time. Well, that's not good. But if I just say 99% classification accuracy, sounds good, let's move on. And it's not always a problem. Maybe in some situations I really only care about my total accuracy, and this kind of error is worth to me the same as that kind of error. And it's not like you have to deal with this 100% of the time. It's not like it's always a problem, but it is often a problem, and it can kind of occur under the radar without you noticing. And it's good to be aware that just looking at classification accuracy doesn't tell the whole story. So there's also more on this in the bonus slides. But the decision theory stuff we just talked about is one of several approaches to dealing with this issue, because you could say, well, if I'm sick and I predict not sick, I want to put a big cost on that because that's very concerning to me. Then I eat something that I shouldn't have and get sick, and now I'm really upset. And if I had a false alarm, maybe I'm not upset. So there are other approaches to dealing with unbalanced training sets, but this is one of them. I think it's a bigger theme in the course. Part of the whole point of this course is to avoid situations where you think you're done and you've got something great, but actually it's not, and that hurts you later, right? So a very straightforward case of that is I just looked at the training error, and that's kind of day 1 of this course or day 3 or whatever. Yeah, you can't just look at training error. But even if you're a little more careful, you're looking at validation accuracy, other stuff can happen. This could happen. You could be misled, or the IID assumption could be grossly violated, and your test data is completely different from your training data. That could happen, and you wouldn't see those things by just looking at the validation accuracy. Okay. I think we did this already last class, so we can skip this. And then finally, some feedback I got teaching the course last time was, could you please just tell me what the hyperparameters are whenever you introduce a new algorithm? So I'll try to remember to do that. I won't say these are all the hyperparameters. It depends on your implementation. It depends on how you even define a hyperparameter. Like with decision trees, there might be different splitting criteria, and you could say that's a categorical hyperparameter. Do I want to split based on this rule or that rule? So I guess, again, speaking of false positives and false negatives, so I will try not to have any false positives. If I list something on there, it's probably actually a hyperparameter, but that doesn't mean I didn't omit anything on the list, because there's a whole bunch of things that could be hyperparameters of the methods. But for decision trees, we had as a prominent hyperparameter the maximum depth of the tree. And often these hyperparameters control complexity. Again, you can define the word hyperparameter however you want, but often it's related to the complexity of the model. So deeper trees, more complex models can capture more complicated patterns. With k and n, we have k as a pretty prominent hyperparameter. And with naive Bayes, we had this Laplace smoothing parameter. I saw there was a question on Piazza about that I haven't had time to get to yet. But beta is sort of related to the complexity, and I think we talked about it at the end of last class as well. So here are some hyperparameters that you could have. Yes, I don't know your name.
Liam.
Louder?
Liam.
Liam.
Why is small k more complex?
Why is smaller k make it more complex? So there's a big discussion about this on Piazza too that I would recommend checking out. I would say, so to summarize what's on there, if you think about it in the extreme, if k equals n, meaning you're just looking at all the data set, then no matter what your test point is, your k neighbors are all the training set because k equals n. And so you'll just see what the most popular label is in the whole training set, and you're going to vote that no matter where in the space you are. So it's like I'm all yes or I'm all no, which is simple. And in the other extreme where k is 1, every little point gets to have its own little neighborhood around it saying, I'm going to vote that near this point. And so it's constantly could be changing, yes, no, or red, blue, or whatever, all over the place. And there's sort of a continuum between the two that's a bit harder to understand. It's harder for me to say in words exactly what k equals 5 is doing, but it's switching from one extreme to the other as you change k. So, by complex, I mean being allowed to change what you predict constantly as I move to different parts of the space would be more complex than, no, I'm only allowed to predict one thing everywhere. Edwin.
Can you explain again what beta is?
Can I explain again what beta is? Yeah, so beta is this Laplace smoothing parameter, which is sort of a fancy name, but essentially it comes from this problem that somebody brought up last class. Ali, maybe? Someone? Brought up last class that if you have never seen something before, like I've never seen a spam message with the word hello, then I'm going to estimate that conditional probability as 0. And then if I see a message, and maybe I've seen one not spam message with the word hello, and then every time I see the word hello, it's just not spam no matter what, because it's 0 times a bunch of things versus non-zero times a bunch of things. And that's not good. So the beta is, you could call it like a pseudo count. It's like pretending to have counted that you've seen something even though you haven't actually seen it. And it smooths out that problem. Because now the difference between seeing 0 and something versus seeing 1 of something, instead of being like infinitely different, it's like I've seen 1 versus I've seen 2. So things don't go as crazy. And by the way, if you go to some machine learning library like scikit-learn in Python or whatever library in whatever package, you will see these things. They might have different names. Like you might look at the scikit-learn documentation, it'll say k-neighbor classifier, and then one of the parameters will be num neighbors or something. That's k. And maybe for naive Bayes, whatever it's called in scikit-learn, it might not be called beta. Maybe they'll call it alpha. Maybe they'll call it something else. And that's kind of an annoyance that people use different notation. But you should start to be able to look at the documentation for these things and match up things you know to parameters that you can pass the code even if they have a different name. Okay, this is a summary of Monday's lecture. We talked about naive Bayes as one example of a more general framework of a probabilistic classifier. We talked about decision theory and a bit of other miscellaneous stuff. And now we're going to move on to today's lecture. Recap of last time, we talked about email spam filtering as a particular motivating example for naive Bayes. And we wanted to put it into our nice world of supervised learning where I have my rectangular X and my Y column, and I've been trying to inject here and there the reality that things are not always this pretty. Your data set may have a different structure, there may be missing values, etc. And we don't treat those issues that much in this course, but please be aware that they exist. So we chose bag of words features. We needed some way of turning an email into a vector because we turn everything into a vector in this course. So we chose bag of words, which is pick some vocabulary of your choosing. I don't know, maybe the 1,000 most popular words, maybe something more clever than that. And then each of those becomes a feature or a column, and then check if the word was present or absent in the email. And just to point out, this is an issue of picking your features. You haven't yet committed to using naive Bayes. You could do whatever you want with those features. Naive Bayes often does reasonably well on this task, but you could take those same features and do KNN if you wanted to, or a decision tree once you have the features. So those are two separate decisions, picking the features and then picking the classifier. So we talked about how we're modeling the probability that a message is spam given the feature vector. We wrote down Bayes' rule. We talked about ignoring the denominator. There was a very good point about this slide being a little bit misleading. Maybe it would be better to say probability of hello and Vicodin and not having 340 in the email equals the probability of having hello times Vicodin times 1 minus the probability of having 340, or the probability of not having 340, because it kind of looks like the number of things you multiply together equals the number of words in that email, but you're really multiplying together d factors every time. And then finally, you predict based on which probability is greater. We didn't normalize them. That's why we just check which one's greater. If I have k classes, here it's just two classes, spam and not spam. If I have k classes, I'll be taking the larger of k probability scores for each class. Okay, so we had a comparison before of naive Bayes and decision trees, so we can have, we've talked about three classifiers so far in the course: decision trees, naive Bayes, and KNN, and this is kind of cute little diagrams of each one. So you could have decision tree, sequential rules based on one filter at a time. You could have naive Bayes, which says, I'm going to make some approximation about the probability of seeing this given the counts of things I've seen. Or KNN says, I'd like to predict for this feature, here's some other point or points that are similar in feature space, so let me just look at their labels and predict based on that. Okay, that is it for review. Any questions before we move on? Ali?
Yeah, going back to the previous slide, just about the conditional independence, I was wondering if you could explain the intuition behind that even more.
Could I explain the intuition behind the conditional independence a little more? So, regular independence, so maybe you thought that seeing the word sale and seeing the word discount, those are two words, right? One assumption you could make is that those things are independent. But that doesn't really make much sense because probably it's quite likely for those to co-occur in email. But that would be an independence assumption. The probability of seeing sale and the probability of seeing discount. But the probability of seeing both is probability of one times probability of the other. That's kind of the mathematical encoding of an independence assumption. A, that doesn't sound right, and B, that's not what we're doing here. We're doing a conditional independence assumption that says, if we already know it's a spam email, then are these two words independent? And that sounds a bit more reasonable because to me, the main way that they would kind of interact with each other is that they're both maybe likely to show up in spam emails. But it's still not quite right, because maybe those words, even within a spam email, tend to show up together. But that's what conditional independence means, as opposed to unconditional independence, is given that the email is not spam, or given that it is spam, these two things occur independently, and the mathematical encoding of that intuition is probability of both, or in this case, we have three things, is just the product of the individual probabilities. That's what independence is, basically, mathematically. Okay, so the motivating application for today is the Microsoft Kinect. For those of you who haven't seen it, it's part of the Xbox system, I guess, and it's a little thing you put on your wall or your shelf. And it has cameras and sensors, and it can kind of figure out where you are, and there's all kinds of games where you can dance or all sorts of things. And it knows, it can track you even though you're not holding any kind of tracking device. So the Kinect works with, uses the method we're going to talk about today. So there's a whole bunch of stuff that has to happen in the Kinect. It has to figure out depths and parts of where's your wrist, where's your hand. It has to do this all very fast. So what we'd kind of like to find today is, well, something that maybe works better than the classifiers we've talked about so far on a whole bunch of problems. Because the classifiers we talked about so far work in some cases, but often have limitations. So ensemble methods is a general umbrella of approaches in machine learning, and random forests are a particular ensemble method, and we will talk about the general and the specific today. So ensemble methods are meta classifiers, or you can think of it as meta learning, in the sense that they take other classifiers as their input and combine them in interesting ways. They have sort of strange names sometimes, so if you've seen any of these words, they may make more sense after today, or they may not. We will talk most about averaging today, and a bit about bootstrapping, or bagging. So we talked earlier about this fundamental trade-off of machine learning between underfitting and overfitting is one way you could think of it, or training error and approximation error is another way you could think of it. And the idea of ensemble methods is, can we get the best of both worlds? Can we take some classifiers we already have and push on one of these sides of the trade-off without hurting ourselves too much on the other side of the trade-off to get a better performing method? We're still talking about classifiers. So in a way, the world of ensembles can be divided into two parts, roughly: the parts that push on one side of the fundamental trade-off and the parts that push on the other side of the fundamental trade-off. It's not precise, the analogy, but it could be a helpful way of thinking about things. So roughly, boosting takes a bunch of underfitting classifiers, and we're going to get into the details, but takes a bunch of underfitting classifiers and makes their training error better. And roughly, sort of, averaging takes a bunch of overfitting classifiers and makes the approximation error. I'm making funny faces because it's a bit more complicated than that. Averaging can also improve training error, but there's something to it. Okay. We will not really talk about boosting because we don't have time. So we'll mostly talk about averaging. At least you've heard of it, which is better than not hearing of it. It's hard with this course because we only have one undergrad machine learning course so far, and there's just so much stuff. And we'd like to have more courses in the future, but we have to prune out a lot of things. So boosting was one of those casualties. Right. So imagine you have 10 classifiers, and for some particular input, these are the predictions. Spam, spam, not spam. Of course, it doesn't have to be email filtering, but any classification problem. It doesn't have to be binary classification. It could be multi-class. So maybe all the classifiers are 80% accurate. So by picking any one of them, I can only get 80% accuracy. The question is, can I somehow combine them instead of just saying, well, this one's the best, I'm just going to use it and ignore the rest? Can I combine the classifiers to make one super classifier? And that's exactly what averaging is. So what you could do, and you could take 3 different things like decision tree, naive Bayes, KNN, and you could just have them vote and then take the output there. If you're wondering about the word averaging, in this part of the course, we've been talking all about classification, which means the outputs, the Y values, are categorical, like ABC, spam, not spam. But later in the course, we'll talk about regression, where the outputs are actual numbers. And then the word averaging is maybe even more meaningful in the sense that you get a bunch of numbers and you literally average them. But the analog of averaging for this categorical outputs is voting. So that's what we're doing here. We're taking some classifiers and having them vote. One thing I just want to say, I don't think is on the slides, but we should have it on the record, is that a big distinction between averaging and boosting, they're very different things. But one thing I want to say is that with averaging, you take the trained models. So you can train each one separately, and then you can average them. With boosting integrates itself into the training procedure. So you're training and boosting all kind of at the same time, which is one reason why it's a longer story to explain. But you take a bunch of classifiers and train them up in a particular way. But here we're just saying, I trained my decision tree, I trained my naive Bayes, etc. And then when I'm done, let me just grab them and average them. Okay, so another thing you can do even fancier than just averaging is stacking. So I could actually fit another classifier whose inputs are the outputs of the previous round of classifiers. So I'm stacking up a bunch of classifiers. And so the decision tree would be trained on, its inputs would be for each training example, what are the outputs of the first 3 things? So these are all under the umbrella of ensembling because they're all meta classifiers or ways to take a bunch of classifiers and combine them and, if we're lucky, do better than each individual one. Edwin and then Miriam.
Isn't stacking exactly the same as averaging then? Because stacking, you have only one feature outputted by the previous models, and those things, it gets input to the, for example, a decision tree, and then obviously it's gonna split on the majority ones.
The question is stacking the same thing as averaging? So no, it's a bit more complicated because well, this is a very simple example that you just have 3 classifiers, but there's all kinds of ways we could extend this. For example, maybe the 3 classifiers output probabilities rather than just yes or no, and maybe we feed that into the decision tree, and it says, I like the KNN, but if the KNN is not so sure, let me look at the, I mean, it could learn that kind of stuff. Or maybe you would allow the original features to influence which of the classifiers you trusted. I'm not sure if that's a common thing to do or not, but in general, it is a more sophisticated approach than just averaging. Miriam?
So it seems that averaging or stacking increases the accuracy of model. What about the performance?
Miriam asked, it seems that this increases the accuracy. What about the performance? So what does accuracy and performance mean to you?
Before explaining this combination of different models, you talked about the trade-off between accuracy and performance of models. I'm just thinking how this can affect these two parts.
I guess you mean like the fundamental trade-off, overfitting and underfitting? Okay, right. So the question is, what do I guess I'm being a bit loose with accuracy. So doing this could improve your training error, and it could also improve your validation error. And I can't say something useful about what's going to happen. And I don't know if that's because I don't know or just because it's not known, but I have seen both of those things happen. So it is often the case that doing this will help with overfitting if individual models overfit, but as we'll see in a minute, it is also possible to just get better training error. So sorry, I basically don't have a good answer for that.
Okay, so is that true that we say combining these models needs more computation, so it is
Okay,
slower?
so performance in the sense of time, definitely. You have to do more work. You have to train more models, and when you make predictions, you have to run more models. So definitely, in terms of computation, yes, this is more work than just one model. And that could be a problem if things take a long time.
So this should be the penalty of increasing the accuracy. Otherwise, how?
Yeah, yes. Usually you'll get better accuracy and it'll take longer. That's the idea. Mohammed.
Yes, I think it's going to do best if the same data coming from the same domain. But if I test on a different data coming from different domain, the weights I've learned through this classifier or the parameters I've learned through the classifier is going to fit to this type of data. Not generalized to other.
So Mohammed was talking about generalizing to data from other domains. Well, that's a challenge whether or not you're ensembling. If you take one model and train it on one type of data, it may not generalize to another type of data, and that's true with or without ensembling. Yeah, let's leave it at that. Okay, fine. Okay, yes, so we'll talk more about the Netflix $1 million prize later in the course when we talk about recommender systems. But the winner of that prize, I know of a whole bunch of competitions. I don't know if you've heard of Kaggle, but it's an organization that puts out these machine learning competitions, and it's very common to see the winners being an ensemble of a bunch of stuff. Okay. Why does this work? Why does averaging work? We're still talking about averaging here. So the idea is that if you have a bunch of models that make different types of errors, then when you're voting, you'll hopefully just iron those out, because one of them will make an error and the rest will be okay on this data point, and so you'll be okay. And then some other data point, a different one will make an error, but it's overwhelmed by the majority. And so in each case, you kind of hope the majority will be sane. On the other hand, if you took the opposite extreme, for example, 10 models that were literally identical to each other, obviously this is pointless because they're all going to vote the same way in every case. So this slide is the one I was looking for, right? So imagine you have models A, B, and C, and you just have 3 training examples, 1, 2, and 3. And model A makes a mistake on the 3rd training example, model B makes a mistake on the 2nd training example, and so forth. And then you vote, then you can see that for the 1st example, you have 2 yeses, corrects, and 1 incorrect, and so you'll be correct, and so on and so forth. So this is kind of a cartoon of why averaging works, because each of my models is only 67% accurate, but my average is 100% accurate. What's your name?
Jeannie? Jeannie.
Judy?
Jeannie.
Jeannie.
Yeah. So let's say model A is more accurate than B and C. Do we take that into account when we're averaging?
Yeah, okay, good question. So Jeannie asked if model A and B is more accurate than B and C. Do we take that into account? So yes, there are weighted versions where, say, one model has more votes than another. Boosting is also doing something like that, among other things that it does. And again, if you're doing regression, so if you're outputting continuous values, you can have a weighted average of the results here. If I had 1.1 votes instead of 1, it might not make a difference, but you can have a weighted vote as well. So yes, that is done. What's your name?
Corinder?
Corinder.
Yeah. Are there restrictions on how the models are trained? Like, do they have to all be trained on the same data set or anything?
The question is, do the models all have to be trained on the same data set? So this also relates to what Mohammed was saying about different domains. No, they don't all have to be trained on the same data set, and we'll talk about that very shortly. Right now. Okay, random forests. So random forests are an average of decision trees. And they tend to work really great, and people like using them out of the box, meaning I don't know much about machine learning. I just take some code from some library on some problem, and I run it, and it kind of works without fiddling with it too much. Random forests tend to be pretty good and fast. So basically, if we take a bunch of decision trees and train them, will they make independent errors? No. So if we just train 20 decision trees on the same data set, we'll roughly get 20 identical decision trees. So we need to inject some variability between the trees so that when we average them, it's actually meaningful. And then to get to Corinder's question, do we have to train on the same data set? So one of these things, bootstrapping, is we're going to intentionally give a different data set to each tree by randomly so-called bootstrap sampling from our original data set. And then each tree has a different data set, but we're even going to inject more randomness than that, which I'll talk about in a minute. So for those of you not familiar with bootstrapping, what we're going to do is our data set has n examples in it. We are going to sample n objects with replacement. So we're getting a new data set. It's the same size as the original one. It's still of size n, but it may contain duplicates. So you may pick example 1 5 times and example 2 3 times, and you may omit example 4 and example 5, etc. But every time you create one of these bootstrap samples, it'll be a different data set, and each tree will be trained on one of those samples. And that'll be part of the variability between trees. So, what's going on here? This is just some pseudocode that says picking a random sample. That's not too critical. Okay, so what we have here is that for those curious, if you do this bootstrapping procedure, approximately 60-something% of the original rows or objects will be included in each bootstrap sample. And the bonus slides calculate that number. But this is a common practice in statistics, because if you do something that's super sensitive to your data set, then you take a bootstrap sample, things will be very different. Maybe you're alarmed, whereas if you do this and things are not very different, then maybe you're more robust. So this word bagging that we talked about before, I think it stands for bootstrap aggregation, and it means take bootstrap samples of your data set, train on each one, average the results. So that's what bagging means. And that is one of the two tricks used in random forest to get diversity in the trees. Connor.
So, sorry, is that a different classifier for each bootstrap sample?
Yes. Is that a different classifier for each bootstrap sample? It is, because each tree sees a different data set, so it is going to learn different rules just by itself, because different data set, you'll learn a different tree. But the tree might not be that different, so we're going to do one other thing to make it even more variable.
So, would you do this where you like fit, say, like one with one bootstrap sample with a decision tree and one with KNN?
Well, the question is, would you do one bootstrap sample with decision tree, one with KNN? So what I'm describing here is random forest, which is a specific thing that involves bootstrap sampling in a specific way, which is you fit a decision tree every time, hence forest. Okay, so the other thing is that every time you split, normally, as we talked about in the decision tree lecture, when you split, you look at all possible features and take the best feature based on the best split. And what you do here is you take a random subset of the features. So maybe you have 100 features. You pick 10 of them at random, and you say you're only allowed to split on one of these 10 features. The other 90 are just off the table. And you do this every time you split, and separately for every tree. So now, even if you were on the same data set, each tree would be different because you're randomly restricting yourself in this way. And you're also using a different data set. So you have these two sources of randomness which work together to make the trees different enough that averaging them is a good idea. Ali.
You choose that small number randomly, or is it one for?
Right, the small number is a hyperparameter. So, and it's a good point for you to bring up because I said I would say what the hyperparameters are. So the number of trees is a key hyperparameter here, and this integer saying how many features I'm going to restrict myself to is also a hyperparameter here. Yeah, what's your name?
Vanessa,
Vanessa?
could you repeat why we're restricting features?
Can I repeat why I'm restricting features? Yes, for sure. So I'm doing that because averaging doesn't make sense if all the classifiers I'm averaging are the same. Because if I just vote and they all vote the same, it's not interesting. So I'm intentionally trying to make my different trees different from each other by kind of messing with them as they're being trained so that when I average them, I get something more meaningful.
And in that case, that makes sense, but wouldn't you lose a little bit of information by taking some of them?
Wouldn't you lose a bit of information? For sure. So each of these trees will be inferior to a regular decision tree because you didn't allow it to do the best thing. And so if you do a random forest with number of trees equal 1, it's not going to be good. But if you do number of trees equal 50, then you hope that you kind of get that power back and better. Okay, so random tree 1, sample 2 features, split on whichever one is best. Yes, okay, so what this picture is showing is what we were just discussing, that you have different trees trained on different data sets, and also what this is showing here, milk and oranges, is that I've restricted myself to, I have to split on one of those two things, and then at this split I restricted myself to egg and peanut, and so on and so forth. So here the hyperparameters would both be 2 trees and 2 features to consider at each split. And again, there could be other hyperparameters if you look at code and stuff, but I'll just talk about some key ones. Whew, 5 minutes left. Okay, so we talked about this, we talked about that, we sort of said it should be good. It tends to do well. People tried a bunch of problems, a bunch of classifiers. These things tend to do a good job. We said that. We said that. Yeah, okay, we said all of this. You take samples of your data set, you learn random trees, you average them at the end. And okay, so that we talked about training. In terms of testing, we have the trees. We don't need to do any sort of bootstrapping. That was for the training. So for testing, we just take our test case, put it through each tree. We get the predictions, and then we take the mode or the most popular prediction. In other words, we vote. Okay. Okay, I have a Jupyter demo, but I'm not going to have time to go through it now, but you can look at it. It's posted as usual, and maybe I'll quickly run through it at the beginning of class on Friday. But I visualize random forests. Okay, so today is the end of part 1 of the course. Part 1, we talked about supervised learning And we specifically talked about classification. We haven't yet talked about regression. So some key ideas from part 1 of the course. We talked about training versus testing, ID assumption. Well, I don't need to read this whole list for you, but we talked about concepts about learning, and especially about the fundamental trade-off. And we made some big distinctions like probabilistic, not, parametric, not. So we're starting to organize these ideas into sort of a taxonomy of classifiers. We talked about the no free lunch theorem, saying there is no model that's best at everything, and that's why we want to study a bunch of different models. And we had some general classes of things, decision trees. We were looking for rules. With naive Bayes, we were counting how much of things we saw. And with K and N, it was based on distances, which, by the way, as I think we've mentioned, is vulnerable to this issue of the scaling of the features. So if one feature contains way bigger numbers than another, anything that involves distances is going to be affected by that, and it's something to keep in mind. And in some cases, the right thing to do may be some pre-processing, like normalizing the features. We also saw 2 ways of generally improving things. We talked about this augmentation of your training set, where you invent fake training data by, we talked about with the images of digits, but doing some known transformation, like shifting the image a little bit that you know shouldn't change the right answer, and inventing a new training example that has the same label as the other one but is a bit shifted. And then today we talked about ensembling in the sense of combining a bunch of classifiers. There's a whole bunch of ensembling. We didn't talk about boosting. We did talk about averaging and a few others a little bit. So I guess I already summarized the whole 2 weeks, but I'll summarize in particular for today, which is ensembles are kind of meta classifiers. Averaging can improve accuracy, but we need the things we're averaging to be different. If I'm just averaging a bunch of identical classifiers, it's not good for anything. And then we talked about random forests as a specific instance of averaging that tends to work very well. So next class we'll start part 2 of the course, which will be unsupervised learning, and we'll start by talking about clustering on Friday. So that's it for today. Good luck on the assignment, and see you Friday.